Welcome to the first lecture in this new series of lectures in group theory. Today we'll be looking at division with remainder, and this really has nothing to do with group theory because this first module, or the 0th module as I'm going to label it, is about recollection or recapitulation of basic number theory. I do not assume that you are familiar with it, even though I call it a recapitulation. This is because elementary number theory deserves its own course, and I will be collecting some very basics of it so that we can use group theory to develop, or rather to prove some number theoretic statements, which we will be able to appreciate only when we have some idea of basic number theory. All right, so let's get started. Since this is the first lecture and this is a level 1 course, I would like to recall some basic notations. So this symbol denotes the set of all natural numbers, and this is that set, and there is not much that I can say about this. This symbol denotes the set of natural numbers appended with 0. This is the notation for set of all integers, so this is how one may denote it. And these two things are called quantifiers. This is quantifiers, ugliness. This is the existential quantifier, and this we read as there exists. This is nothing more than a short form for this phrase. Every time writing this phrase is cumbersome, so we just use this symbol. Similarly, this is the symbol for all. All right. This is the symbol for belongs to or in, so we may write x belongs to A or x in A, where A is a set and x is an element of A. This is the notation for the empty set, and this is the notation for subset, so we may write A subset of B. This is the notation for proper subset, so when we write this, we mean that A is contained in B, and there is some element in B which is not in A, so it's a proper containment. Alright, great. So what is the well-ordering principle? The well-ordering principle says something very intuitive. It says that if you take a non-empty subset of the natural numbers, then it has the smallest element. Let me expand on that. So that just means that there is some element in S, which is smaller than every other element in S. So that's what it means to have a smallest element. And this is very, very intuitively obvious, so I can't say much in the way of proof of it or any such thing. I hope you immediately grasp what this is trying to say. So here is a very simple exercise. Show that if S is a subset of now this guy, this is not a set of natural numbers, this is a set of whole numbers. So I should have said this is called the set of whole numbers. So if S were a subset of whole numbers and it is not empty, then show that it has the smallest element. Of course, this is as intuitively obvious as the previous one and as easy to prove as anything can get, but still, I have posed this as an exercise. Alright, so now let us get to some basic definition about division which we learned in high school. So we have two integers and one is non-zero, A is non-zero. Then we say that A divides B if there is some integer q such that B can be written as the product of A and Q. So of course we are familiar with it, and note that I am allowing for negative integers. Alright. So that's one thing, and now there are some synonyms. So we say that A divides B, or we say B is divisible by A, or we say that A is a factor of B, or we say that B is a multiple of A. All these things mean the exact same thing. Okay. So this is a notation which we will use frequently. If A divides B, then we will write this, because writing this every time is cumbersome. So remember this notation. We'll use it frequently. And now here are some basic properties that one can easily observe, or these one can take as exercises. So if A divides B and B divides C, then A divides C. Note that whenever we say A divides B, we already mean that A is non-zero. That is only when we have defined division. This is called the divisor, and this always has to be non-zero. This guy can be 0. The one that is being divided can be 0. 0 is divisible by every non-zero integer. So whenever we say A divides B, it's already assumed that A is non-zero, and when we say B divides C, it's already assumed that B is non-zero. So then one can formally show that A divides C, and I leave that to you. And similarly, there are these other, sorry, what happened? Yeah, so there are these other exercises. 1 divides every integer, obviously. 0 is divisible by every non-zero integer. If you have a non-zero integer, then it divides itself. And if you have two positive integers and A divides B, then the dividend is at least the divisor. And all of these things, of course, we are familiar from high school, but one should properly write down proofs of it using this formal definition. I'll leave that to you as an exercise. All right, great. So let me also introduce the notion of primes, a very fundamental concept in mathematics. So we have pick some positive integer, which is greater than or equal to 2. So we say that such an integer is a prime if the only positive factors of P are 1 and P. So note that if you have some integer n, then, or let's say positive integer n, then it has 1 and n are of course positive factors of it. But primes are those for which these are the only positive factors. And I'm sure you are familiar with the notion of primes, so I will not spend much time on it. And these are the examples of primes, and you can go on. And there are infinitely many primes, as you might already know, and perhaps we'll give a proof of it, proper proof of it in the course of these lectures. Okay, and now I want to get to the main theorem of this lecture. So this is called division with remainder or division algorithm or something, but I will just call it division with remainder. So we have two natural numbers. Then there exists there's a unique integer q and an integer r, so I should say integer. So unique q and r in Z such that first of all, b is equal to dq plus r. So what is it saying? It is saying like dividend is divisor into quotient plus remainder, that kind of thing. And that this remainder is in this range. So note that this is not saying anything very surprising. This is intuitively very, very obvious. So for instance, suppose you have d equals 2. Let me use a different color. So let's say you have d equals 2. And let's say b is 7. So then you can write 7 as 2 times 3 plus 1. This remainder, this 1 is the remainder when you divide 7 by 2, and this is of course less than 2 and greater than or equal to 0. So we are just formally saying this thing that we have a very good feel for. And it may seem like a frivolous thing to even try to prove it, but to give a formal argument of this may not be immediate if you haven't seen these things, or if you're seeing these things for the first time. A formal argument is a piece of language which dispels all doubt as to the veracity of the proposition without betraying some month-long constipation. So let us be very, very clear and cogent in our reasoning so that this thing just dissolves under the weight of mathematical argument. All right, so here is how we do it. This is one way to do it, and in the next lecture I will give an alternate way to do it. But let's concentrate. Okay, so we define the set S as b minus dq, where q is in integers. So this is, I'll say something more here, but what is this? So we collect all the possible differences that you can get as you vary q over all the integers. So sort of, in some sense, we are collecting all possible quote-unquote remainders, but we will be only interested in the non-negative ones. So basically, what is S? S is all these kinds of numbers that you can form when you choose an integer q, but you only collect those ones which are non-negative. You throw away the negative ones. So this is a set, and of course this is a subset of a set of whole numbers, of course. And now, by the well-ordering principle, well, first we need to show that this is non-empty. So why is it non-empty? It is non-empty because you could choose q equals 0. If you choose q equals 0, then b is of course a positive integer. It is a natural number which lies in, which of course, I mean it is there in this set. So S is non-empty. Let me just write that. Thus b in S, and hence S is non-empty. And now, by the well-ordering principle, we know that, or we have a smallest element call it R in S. So obviously, thus this is obvious because R lies in the set of whole numbers. We've chosen something which is smallest in S, and S is a subset of this guy. So R is non-negative. So what we want to show is that R is less than D. Okay. So suppose not. So this means that assume that R is greater than or equal to D. And now, since R is a member of S, we can write R in this fashion. So let q be some integer such that R equals b minus dq. Such an integer must exist because R is after all an element of S. It is the smallest element of S. Great. But if R is greater than D, then we get R minus D is b minus t times q plus 1, which is, this is non-negative. This guy is non-negative. Why is it non-negative? Because of our assumption that, R is greater than or equal to D. So because of that, this is non-negative, and hence, therefore, R minus D is also in S. It is a non-negative integer which can be formed via this kind of a number here, because you just have q plus 1 here. So it can be written as b minus d times some integer, and it is non-negative. So it is in S, and it is of course smaller than R because D is positive. But R minus T is strictly smaller than R, contradicting the minimality of R. Right? R was the smallest element of S, but R minus D is further smaller than R, and it is also in S, as we argued, so it is a contradiction. So therefore this assumption must be false. The assumption that R is greater than or equal to D must be false, and we have proven this. So we have proven the existence of such an R. Basically, we have proven these two things, that there do exist Q and R such that this happens, but there is one more thing in the proof, which is the uniqueness. So far we have just given the proof of existence. So we need to give a proof of uniqueness. So for uniqueness, suppose B equals dq1 plus r1 and B equals dq2 plus r2 for some q1, q2 in integers and r1 and r2 with this constraint. So we want to show that q1 equals q2 and r1 equals r2. So this is what it means for the decomposition to be unique. So how do we do this? So by these two equations, 1 and 2, we have 0 equals d times q1 minus q2 plus r1 minus r2. Okay. What did I do? I just subtracted the two equations. Okay, fine. So we get r2 minus r1 equals d times q1 minus q2. So if q1 were equal to q2, so if q1 were equal to q2, then r2 would be equal to r1 because this side would become 0. So we may assume that q1 is not equal to q2. So may assume, because otherwise we are done. So may assume that, or rather, okay, so let me argue this way. So if q1 is not equal to q2, then let me take absolute values on both sides. Equal to that thing, which is greater than or equal to d. Why is it greater than or equal to d? Because this is at least 1 in the absolute value. So this thing is at least d, but this guy is strictly less than d. This person is strictly less than d. So this gives that d is greater than or equal to d. So why is this strictly less than d? Because of this constraint. I'll leave that to you to figure out. It's not at all hard. So this is of course a contradiction. So let me say it this way. So if this were the case, then we would have, which is a contradiction. So if this, then this, which is a contradiction. Or which is absurd. So therefore, q1 must be equal to q2, and hence by star r1 equals r2. So we have shown both the things that we wanted to show, and that's it. So this proves uniqueness of the decomposition. So once again, given positive integers b and d, there are unique integers q and r with these two properties. there is such a pair Q and R, and there is only one such pair. Alright, so this is called division with remainder, and this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe. I also have Patreon, the link is in the description below. Thank you for listening, and I'll see you next time.